Okay, for this review, I'd like to take a look at the concept of internal heat generation, and we'll look at it with regards to how it applies to the heat transfer rate through a one-dimensional plane wall. So the geometry that we're going to be looking at is shown here. We have the center of our coordinate system, x equaling 0 at the midplane, and the width of our plane wall will be 2s, and we're allowing for the temperatures at the wall to be different temperatures, and as I've drawn the purple line in here, this is the temperature field that we're looking to solve for. So the way we're going to go about doing this is starting with the heat equation, and in this drawing the heat equation this way, it is essentially it's a modification of Laplace's equation where this constant term here, Q dot over K, accounts for the internal heat generation. Now the general solution to the heat equation takes the form of a quadratic, and it has two unknown constants, C1 and C2, which of course come from the fact that this is a second order ordinary differential equation. We'll also notice that it's a negative quadratic, so the shape of our temperature curve is drawn incorrectly, and of course this is what we would expect because the walls are going to be held at lower temperatures than the internal temperature of the wall itself. So we'd expect this, we'd expect essentially the center of the plane wall to be at a higher temperature than either of the end planes. Now, applying the boundary conditions that we've essentially established in our sketch over here, we will find out that the general solution, or the particular solution rather, for the temperature field can be written as this. Again, it's a rather simple quadratic, but it has enough terms in it, and but again, the only variable is x, and the shape of the quadratic will be modified by our choices, relative choices of T1 and T2, and the amount of internal heat generation. Now, the temperature gradient we arrive at by taking the first derivative of the temperature field with respect to x, and we find out that our temperature gradient is dependent upon the variable x, and it's also important to note that if the internal heat generation Q dot was equal to 0, the temperature gradient would just reduce to that of a simple one-dimensional plane wall with different temperatures on either side of it. Now, the rate of heat transfer is going to be given by taking the term that we have for the temperature gradient and allowing us to substitute this back into Fourier's law. And again, in this case, we'll carry through our unknown area of the wall. And we come out to this rather simple term, or expression, and we can now apply this simple expression to determine the rate of heat transfer through both the left-hand wall and the right-hand wall. And we do this by substituting in for the one variable here, x, either a value of minus x or a value of positive x. And the results are written here below, so we get just a slight variation on a theme with regards to what the heat rate is out of each of the particular walls. And returning back up to our diagram here, we'll see that as we would expect with internal heat generation, we are able to transfer heat through both the left-hand wall and the right-hand wall, and they do not need to be equal quantities. The rate of heat transfer will be driven by the temperature at which the surfaces are held at. Another thing that we want to take a quick look at is that there is a special case where the temperature gradient can equal 0, and if we allow the temperature gradient at x equaling 0 to equal 0, that's going to imply that T1 equals T2. So essentially, if there's no heat transfer through the midplane of the wall, which is the case when the temperature gradient equals 0, then we have an equal temperature distribution on either side of the wall, and likewise the heat rate leaving through each surface will be equal to each other. We can also think of this as the center line being a line of symmetry, so that we could only have to solve for one half of the problem, or we can also say that one side of the wall is adiabatic. So again, we could solve this for just this left-hand side and consider the right-hand side as being an insulated wall. And the last thing we want to take a look at is that the equation that we're left with over here for the rate of heat transfer through the plane wall could also be written in terms of a heat flux, where we've divided through by the unknown area A, and we allow for our length and thermal conductivity term to be combined into a thermal resistance. All right, so this ends our quick review of internal heat generation.